Okay, so thanks so much for the nice introduction. And of course, first of all, I need to say thanks to Winston for this nice arrangement. And it's really very pleasant for me to come back. And 2 years ago, I visited this Winston's group and also gave a seminar here. Right. The two topics are very similar, but now it's something new compared with the last talk. Okay. Yeah. So in this talk, I'm going to. Actually, for me, I do both the condensed matter and cold atoms, but in this talk, I will only focus on the condensed matter. It's purely condensed matter. So the title is the non-abelian braiding of Majorana Kramers pairs. So I will tell you why for the Majorana Kramers pairs you can have non-abelian, and I will tell this story. So the work is mainly collaborated with the two graduate students, Pinga and Yin Pinghe, from the Peking University. Okay. Okay, yeah, this is my center. It is called the ICQM, the International Center for Quantum Materials, from the Peking University. Okay, let me give a very brief introduction to the Majorana fermions. And probably many of you guys have heard of this similar introduction from many other talks. So, but maybe for some of you are still not very familiar about the Majorana fermions. So I still give some introduction. But if you are really very familiar, okay, just maybe you can take a lap for some minutes. Okay. Yeah. So the motivation is actually from this particle is called the Majorana fermions. Why? So and what is Majorana fermion? Actually, this concept that comes from the elementary particle physics. From the Dirac equation, we know we are familiar with the complex solution. We know for the complex solution of the Dirac equation, the psi should not equal to the psi star. So the picture is quite simple, namely that actually you have the electron solution and also positron solution. They are complex solutions. The electron and the positrons are different. They are opposite particles. Okay, they are not equal to each other. However, Majorana just did some modification to this Dirac equation. He rewrite this gamma matrix in terms of complex representation. It's fully complex. So if gamma mu is complex, then the equation becomes a real. So in that case, you have the real solutions. For the real solution, of course, the wave function psi should equals to psi star. If you write down in terms of the operate, it calls that gamma equals to gamma dagger. This means that in this case, the particle and the antiparticle, they are the same. They are identical. Okay, for the particle and the antiparticle are identical. This is not strange for bosons, for example, for photon. Okay, there's no difference for the photon and the antiphoton, right? But for the fermion, this really is very special. It's quite special. It's not common. Originally, Majorana wanted to use this idea, this concept to interpret neutrinos, but so far we still do not have a confirmative answer to this issue. However, now we want to try to discover this particle in the condensed matter physics. Of course, in condensed matter physics, for the elemental particle, we only have electron. So to have the Majorana fermion realized in the condensed matter system, we can only obtain some kind of quasi-particle, which might be a Majorana fermion, right? So, however, in condensed matter, we know for the electron, we also have an effective picture for the hole. The hole can be understood as the antiparticle of the electron. Then a possible combination that if you combine the electron and the hole, okay, you can get a quasi-particle which is Majorana fermion. Okay, so then to have this kind of quasi-particle, we can soon think that maybe we can obtain this kind of quasi-particle in the superconducting systems. But furthermore, actually, this kind of Majorana mode may emerge as a zero-energy quasi-particle in the pure topological superconductor. In that case, for this kind of pure superconductor, if you have the zero energy excitation, it should be a Majorana fermion. Okay. But more interesting, we want to study this issue in the condensed matter. The reason is because the Majorana zero bound states in the topological superconductor obey non-abelian statistics. Actually, this is the most important motivation why we want to study Majorana fermions in the condensed matter. Okay, I will go back to this issue later. Okay, first of all, why, as I just mentioned, in the pure superconductor, we can have the Majorana fermions. How to understand this picture? So actually, suppose, this laser pointer does not work well.
Run a battery?
Yeah, I guess.
We get some battery.
Right. Okay. Yeah. For example, this here is a very simple picture. Maybe most of you guys have heard of, you know this picture before, maybe. For example, in the SOL superconductor, the superconductor you can say that this electron equals to the whole plus equal pair. So the left equals to the right. This is just identical. It's an equality. However, in the superconductor, the equal pair, you cannot see the equal pairs condense. So it condense to the ground state. So you cannot see the equal pairs. Okay. So or equivalent, you can say that the pairing will induce a coupling between the electron and the hole. Then in that case, the quasi-particle in the superconductor should be the superposition of the electron and the hole. However, this quasi-particle is the C up plus C down. Is the electron up plus hole down. So then this kind of quasi-particle should not be a Majorana fermion since C up and C down are different. Okay. So then to have the Majorana fermion, you can imagine that you should kill the spin degree of freedom. Okay. Then suppose we can have a spinless pure superconductor. Then you have the similar equality. The electron equals to hole plus this equal pair. Again, the equal pair condense. So actually, this equal pair, the pairing induces the coupling between electron and hole. Then the quasi-particle becomes the C plus C dagger. This kind of quasi-particle. So when this coefficient satisfies some condition, it becomes a Majorana fermion. So this is the simple picture why you want to search for the pure type superconductor, and then you can have the topological superconductor obtain the Majorana fermions. Okay. So this is the simple motivation. So then. So far, there are many different kind of systems they are predicted in theory, which can support Majorana fermions. Actually, the first example is called the fractional quantum Hall states with the Fermi factor 5.5. Actually, for this system, you have many different possible ground states. Only for the far-field state. For the far-field state, you can have the non-abelian phase, and the quasi-particle will be a Majorana fermion. Okay, but the second example is the P plus IP superconductor, and almost in the same time, the Kitaev proposed a toy model for the one-dimensional case. You can also obtain the 1D pure superconductor, and all these issues are corresponding to the intrinsic pure pairings. But recently, people are interested in the effective pure pairing based on the proximity factor, and in that case, actually, the system, you combine the spin overcoupling and the conventional SOL superconductivity. Then you can see that the spin overcoupling can drive the SOL into an effective pure pairing. So this is the basic idea. And there are many studies. Actually now there are many new studies and also a lot of experiments, including the experiment by Seger and the co-authors. Colleagues. Okay, but so far we still do not have a very confirmative conclusion. Still ongoing, also I would like to also mention some recent developments in the PKU groups, and we consider the superconductivity induced in the dioxide metals and Y7 metals, and why we think maybe this kind of materials could be interesting to study the topological superconductor. The reason is because for this kind of materials, the Fermi surface itself is topological. You have a metallic Fermi surface, and the Fermi surface is topological. it's already topological. Then when you induce the superconductivity in this kind of material, you have some chance to get the pure pairing or the topological superconductivity. And actually in the experiment, they measured some interesting pure type pairing, and we also have some theory to propose that in this kind of material you can obtain the topological superconductivity. Anyway, okay, this is the most recent one paper. We just posted on the archive. Right. Okay, yes.
For the purpose of creating some topological superconductivity, does the dioxide metal make a difference from the Wilson metal? Does it make a difference?
Actually, have some difference. The good thing that for the wire semi-metal, at each wire point, for each wire cone, you have definite chirality. So it's actually protected by the two number. But for the dioxide metal, for each drug point, you actually have double degeneracy. You have two. You can see it combined by two wire cones with opposite chirality. In that case, you have more possibility to get different superconducting phases. It might be trivial or non-trivial. But in wire semi-metal, personally, I think that it can be more natural to get the non-trivial case.
So for the direct metal, semi-metal case, when you try to induce superconductivity, is the density state too small for having higher critical temperature?
Yeah, this is a good question. So that's why in the both materials, you don't have intrinsically you don't have superconductivity. In the experiment, they use the point contactor, a hard tip point contactor, to induce superconductor in this material. Probably that when you exert a point contactor, a tip on the material, this tip can exert pressure on the material, and maybe this pressure can give some doping effect or some other effect. I'm not sure. Then this will induce the superconductivity. Yeah.
Does that depends on where your chemical potential lay out?
Right, but for these materials, actually, you cannot control the chemical potential. It's really the bulk material. Anyway, you grow the material there, and then you input a tip. Actually, if you find that this really depends on what kind of tip. If you use a soft tip, or if you use a hard tip, it can induce different pressure, and only in the hard tip you can induce the superconductivity. If you use the soft tip, then the pressure is small. You cannot. We don't observe the superconductor.
So I also have questions that how special are those well points and Dirac points in terms of realizing topological selectivity? Because even for the much conventional Echelon, you can get topological selectivity.
Right.
So I wonder what kind of unique aspect does the well points or Dirac points offer, or simply because those materials have very large spin open interaction on the Fermi surface.
Right. Right.
Which one is?
Actually, for the both the wire semi-metal or Dirac semi-metal, the key thing that at the Fermi surface, the Fermi surface itself is non-trivial, is topological. This is I think this is the most important difference. That means that if suppose for Fermi surface, if you have non-trivial topology, then if you induce the superconductivity on this Fermi surface, if you just consider the normal BCS type pairing, then you can imagine the superconductor pairing cannot change the topology of the system. Then the topology of the original normal state can go to the topology of the superconductor state. So this is the one picture to understand why this kind of materials might be good to realize the topological superconductor. Yeah. Right. Okay. So there's of course you can study the similar issues in the cold atoms. Actually, there are many developments in the recent years. Also, besides this kind of studies, Vincent's group also studied the topological superfluid in another way, based on for example, the interaction to induce the non-trivial superfluid. But here, a similar case that you can use the spin overcoupling plus SOL superfluid and the Zeeman field. You can also realize the topological superfluid. It's fully similar. However, in the case that encode items, actually you don't have spin overcoupling. Remember, so first of all, you need to have an idea to realize spin overcoupling. So recently we do have a very good experimental process to realize spin overcoupling in code items. The first experiment was done in 2011 by Nisler group, and now there are many routine experiments to realize the one-dimensional SOC. But before last year, we only had one-dimensional SOC in code items. Actually, that's not enough to realize the topological superfluid in code items. Since in code items, to obtain an intrinsic superfluid, at least you should have two-dimensional case. The one dimension you don't have non-linear order, right? So then actually you need to have a 2D SOC. But this is quite non-trivial. And recently we proposed an idea, and this has been realized in a recent experiment. Yeah. So this paper is still in the second round review in Science. We hope this can come out soon. Okay. Yeah, just now I give some background for the progress of this issue. But I can quickly go through the basic idea to realize the P-well superconductor. The simple idea is the one-dimensional case is given by K-type, and this the PDG Hamiltonian is quite simple. It's just a polymetric. It's a two-by-two Hamiltonian. And to understand the topology of this system, you can see that actually this pairing, these terms, for this Hamiltonian, you can see that this H can define an effective Zeeman vector, like that in the moment space. Also, it just goes through the K space. You can see that this moment space can give a mapping between the K and to this cycle. Okay, so you just simply check this. This model is very simple. If the chemical potential is negative, this mapping will cover 0 times of this cycle, so it's trivial. But if the chemical potential is positive, it's called the weak pairing region. And then this mapping can cover a 4 time of the cycle. So in that case, it becomes topological. So when it is in the topological region, you see that in the bulk it's topological, but in the end you have a Majorana bounded state localized in the end. Okay. Okay. So this is a very simple picture. I'm not going to discuss more details since this is very very simple, and I guess most of you guys are familiar with this theory. If you are not, you can stop me and ask me. Okay. So, but now the case that we now, as I just mentioned, now people are most of focus on the proximity effect. So the idea is that you consider an SOL box superconductor and consider an SOL, or consider a non-Y on the superconductor. So this superconductor will induce superconductivity on the non-Y. And in the non-Y you have SOC, and furthermore you should apply a Zeeman coupling. So then how to understand in this system you can learn as a P-well superconductor or topological superconductor. The idea is also simple. So suppose in the system in the non-Y you don't have spin overcoupling. You only have the Zeeman splitting. Now in this case you have two split bands, spin up, spin down. Now then when the family energy is here, the SOL parent cannot do anything, since the SOL pair must happen between spin up and spin down. So then it does not open a gap in the Fermi energy. Now furthermore, you open the spin overcoupling. Once you have the spin overcoupling, the spin is not fully polarized. It depends on the momentum. So for the left Fermi point and other Fermi point, they're not fully polarized. They have some opposite direction. So in that case, the SOL pair can happen between the between the K and the minus K. So then the SOL can open a gap in the Fermi surface. So then how to understand the P-well? Suppose this pairing, of course here you have a Zeeman gap here. Suppose the pairing between the SOL pairing is small compared with the Zeeman gap. Then you can forget about the pairing between the lower band and up band. You just consider the pairing between the Fermi states, Fermi energy states. So then you can do a simple projection. Just project the pairing into the Fermi surface at the Fermi surface. So now once after the projection, you can imagine the system becomes an effective spinless. Once you have this effective spinless pairing, it must be factor P well, and then you should get a topological superconductor. Okay, then you get the Majorana bound state. Okay, there are important experimental progress based on this idea. So the first experiment was done by Seger and Covenhoven and the colleagues, and also other experimental studies. And also there are many recent, not many, there's some recent further progress on this issue. But so far, it's still not confirmed, since we need to have better signatures to confirm the Majorana fermions. And Seger is doing this, is working on this, and I think he has many interesting progresses. Okay, yes, yeah. Okay, now I should go a little bit faster. Now we go to the time-Rosen invariant case. Just right now we have the chiral period superconductor. In the previous cases, in the non-Y, the time-Rosen symmetry is broken. For the topological case, at each end you have a single Majorana bound state. Now suppose we consider time-Rosen invariant case. That means that just you combine two copies. For a single copy, at each end you have a single Majorana fermion. So then we can combine a time reversal copy. This one is a time reversal copy of this one. So then then at this end you also have a Majorana fermion. So combine them together, you get a time reversal invariant topological superconductor. Then at each end you have two Majorana fermions. Oh, that's very simple. So then you just you worry that the two Majorana fermions can couple to each other, then split out, becomes a complex fermion. It doesn't, since you have time reversal symmetry. The time reversal symmetry should protect Kramers pairs. So because of this time reversal symmetry protection, is still protected. So at each end you have a single pair of the Majorana fermion. So this is protected by time reversal symmetry, and the classification is Z2. Okay, the physical picture is quite simple. Okay, now there are also many proposals to realize this kind of time reversal invariant topological superconductor. But however, so far we don't have experimental studies on this issue. There are many reasons. Maybe one reason is because you should have good motivation why you want to study this time reversal invariant topological superconductor. Okay, maybe the talk in the study in this talk should give you some motivation maybe. Okay, now okay, I'm going to the non-abelian statistics. So actually the statistics corresponding to the braiding rule for the particles. So we are familiar with the bosons and the fermions, or abelian aliens. In those issues, when you braid the two particles, you get a phase. Okay, for bosons, the phase is 0. For fermions, it's pi. For aliens, it can be any kind of phase. Okay. But anyway, this is the U1 phase. For U1 phase, is a U1 group, is an abelian group. Therefore, it's abelian. Namely, if you braid 1 and 2, and then 2 and 3, it's equivalent to first you braid 2 and 3, then you braid 1 and 2. It doesn't matter. But for the Majorana fermions, it's quite different. Now, a single Majorana fermion cannot have a well-defined Hilbert space. Only you should always pair the two Majorana fermions. When two Majorana fermions can combine into a complex fermion. For a complex fermion, you have a qubit, since a complex fermion has two states, 0 and 1. Okay. Now, actually, in this case, you can call that a single Majorana fermion has a irrational quantum dimension. It's square 2. You don't have an integer quantum dimension for a single Majorana fermion. Actually, this is why you say that you have the non-abelian statistics for the Majorana fermions. Okay. Now, the picture is quite simple. That consider you have two Majorana fermions. It can be described by the branch cut. Since it corresponds to the vertices. When you braid the gamma 1 and the gamma 2, you can see that gamma 1 cross the branch cut of the gamma 2, but gamma 2 does not cross the branch cut of gamma 1. Then in this braiding process, gamma 1 should go to minus gamma 2, but gamma 2 still goes to gamma 1. So this process can be simply described by this braiding operate. So in this two Majorana fermion case, this braiding operator can be described by this matrix. It's 1 and I. So in this quantum states picture, 0 goes to 0 and 1 goes to I1. So it's diagonal. it's still this braiding operator is still diagonal. This is fine. Since here you only have a single qubit. In this case, you should, of course, it should be diagonal. But anyway, it's the matrix. So for the matrix in general, it should be non-abelian. It's different from the U1, the group, right? It's a matrix. But if you want to really see the non-abelian, you can go to the 4 Morphemeans. In that case, you have two qubits. 1 and 2 combine a qubit. 2 and 3 and 4 combine another qubit. Then if you do the braiding between 2 and 3, you can see that the initial products they can go to an entangled state. So this is a very simple result. So this means that based on the braiding, you can manipulate your states, and this might be good to be used for the topological quantum computation. This is why we are interested in the Morphemeans. Okay, this is for the 2-dimensional case. For the 1-dimension, Jason, Alicia, and the co-authors proposed to do the braiding, but in that case, you need to apply a junction. Since for really a single nanowire, you cannot do the braiding. You must consider a junction, but based on junction, you can do the braiding in a similar way, and you can prove the braiding is the same as the braiding in the 2-dimensional case. You get the similar results. So then it means that you can use the Majorana nanowires to do the braiding and to the topological quantum computation, maybe. Okay, now I'm going to. I have a non-introduction. How many minutes I have done? Oh, half an hour. Okay, good. Yeah. So now, this is my main motivation to study this issue. So what about the time-erosion invariant topological superconductor? Okay. Yeah. First, for the braiding of the Kramer space, we need to have a definition. So the definition actually means that we braid the 2 Kramer space but without the local operations of the 2 Majorana modes in a single Kramer space. So we only the braiding the 2 Kramer space, but we don't do the operation on a single Kramer space. So this is the definition. Okay. So but maybe you can see that you can imagine that. Okay. For the time-erosion invariant topological superconductors, at each end we have 2 Morphemeans. So, but at each time when you do the braiding, actually you braid 2 pairs, not braid 2 isolated Morphemeans. So then, as I just mentioned, that if 2 Morphemeans can combine a single complex fermion. So it looks like that you just braid 2 complex fermion, and then it should be trivial, and then you should not get non-trivial results. But actually, this is not true. The key thing that based on this definition, we do have non-trivial results for this braiding. So actually, we can first of all we can prove this result based on this definition. So first, to understand the braiding rule for this process, we only need to figure out how the qubit states evolve during this after this braiding. So for here, since we have four Morphemeans, you have 2 qubit states. So then you have the 4 states 0, 0, 1, 1, and 0, 1, 1, 0. So during this braiding, we can obtain that this braiding 0, 0 should go 0, 0, and 1, 1 should go 1, 1. Since they are time-erosion invariant states, therefore after braiding you don't have a phase. However, for the 0, 1, and 1, 0, they should have a phase, but they are time-erosion partners. So this one should be phi, and that should be minus phi. Okay. Yeah.
So these indices 0 and 1, should I think about the pairs sharing a fermion, a real fermion?
Which one? You mean the 0?
0 and 1 in the ket.
Right.
Do they mean that there is a fermion and a pair of Majoranas, these zeros and 1, or what do they correspond to?
0 corresponds to the qubit state for the gamma 1, gamma 2. 0 tilde corresponds to the gamma 1 tilde and the gamma 2 tilde. Yeah.
What about tildes? Minus 1?
Which tilde?
Like 0 with a tilde?
This one?
Yeah.
0 tilde means the is a quantum state for the complex fermion which combined by gamma 1 tilde and gamma 2 tilde.
Okay.
Right. And so 0 means it's a quantum state for the complex fermion gamma 1, gamma 2. But 0 tilde is the quantum state for the complex fermion combined by gamma 1 tilde and gamma 2 tilde.
Okay, so tilde
Right.
is always the second position.
Right. Yes. Okay. So then we just need to figure out what's the phase of this one. So to obtain this result, we can simply prove a result. If we braid force, this braiding must go back to the original one. So this means that the U cortical should equal to 1. Okay. So in that case, then phi can only take 3 possible values: 0, pi half, or pi. Okay. Then furthermore, we can consider a special case. Consider that suppose that this time Rosen invariant of superconductor are combined by 2 decoupled copies, just for the 2 decoupled copies. Okay. Then in that case, you can simply know that this phase is pi half. And then for the general case can be continuously deformed from the special case. You change the parameters. But during this continuous deformation, the discrete value cannot be changed. So this means that in general case, this phi should always equal to pi half. And then under this result, you show that this braiding reduced to this one. This looks like that this braiding is reduced to braiding of 2 independent copies, just like that. Okay, but then once based on this braiding operator, actually you get the non-abelian. So this is the okay. Maybe you will worry about it. Okay, this looks like that. Just 2 copies. What's the new? Actually, we have new, but here I'm not discussing what's new you can obtain. Just tell you the results for the operator. Okay. Okay. But remember, this is a definition. The key definition that you only do the braiding for the 2 Kramer space. You don't have local rotations. You don't have local operating. This is the key thing. Of course, once you do this definition, this is the right definition. It's mathematically true. It's fine. But now we should worry about the physical results. So in the physically, maybe we want to ask some questions. What are the sufficient conditions for the non-abelian braiding of the Kramer space? I mean, what are the sufficient conditions? Under these conditions, when you do the braiding, you only braid the 2 Kramer space. You don't have local rotations. So you must ask this kind of question. Maybe you can guess the condition. Maybe you say, okay, if you have the time Rosa symmetry at every time in the braiding, okay, is this enough? But the answer is no. So actually, there are some recent studies. Actually, this our work generates a number of discussions. So these guys discuss a situation that they consider the system, but they preserve time Rosa symmetry at each time, but they consider time-dependent perturbation. Okay, but then they say that even you do not break time Rosa symmetry at each time, but still you induce local mixing between 2 Majorana fermions within a single Kramer pair. Okay, then this gives rise to some questions. You must find a way to rule out the random local rotations in a physical system. Otherwise, you cannot obtain this non-abelian braiding, and it's not possible to observe this non-abelian braiding. So it's,
Let me make sure I follow. So you assume the operations of the time-Rosa symmetry, the braiding operations of the time-Rosa symmetry.
right, you have time Rosa symmetry at every time, at each time. Right, yeah. So, but you have time-dependent perturbation for them in that case. Then
If you do it arbitrarily slowly, it's okay.
it doesn't matter. Right, even arbitrarily slowly, you still have local rotation. It's not a dynamical issue. It's actually a geometrical issue, geometrical effect. Right. So then we should figure out. So first of all, we should figure out the sufficient conditions for non-abelian braiding of Majorana Kramer space. So furthermore, we should ask how well such conditions be satisfied in the real physical systems. So, or suppose these conditions are not satisfied, how bad the system will deviate from the ideal situation. Yeah, this is the two questions we should answer. Okay, now actually we figure out the answers, but now first we present the sufficient conditions for the braiding. These issues are somewhat mathematical, but I just give you the results. Okay, and so, okay. The first, actually, we have a number of conditions. The first condition, okay, of course, we should have the time Ross symmetry at every time. Okay, suppose you consider a braiding, which should be described by a time-dependent Hamiltonian, or you should braid the system, and at each time you have time Ross symmetry. So once you have this condition, then you can make sure at each time you have a Majorana Kramers pair. Okay, this is, of course, this is the first requirement. So the second condition is we should have the adiabatic condition. Oh, this is for sure. This is required for all the braiding, right? Even for the braiding without for the chiral topological superconductors, you should always have the adiabatic condition. But this means that the braiding time should be long enough with respect to the 1 over the gap. Then you should not have the excitation. You excite the ground state to the excited states. Okay. Then once you have this adiabatic condition, the good thing that you can consider the braiding within the subspace of the 4 Majorana Kramers pairs. Okay, the 4 Majorana fermions. Consider the braiding for the 2 Kramers pairs. Now, if you're under the adiabatic condition, you don't need to worry about the excitations. You only consider the 4 ground states. Okay. Then in this case, then we can study this braiding operation within this subspace, and then we can rewrite this braiding transformation in terms of an effective Hamiltonian. We can define this braiding transformation into based on an effective Hamiltonian. Okay, then that means this effective Hamiltonian describes the evolution for the 4 Majorana fermions. So this can be simple. The original Hamiltonian is very complicated in general, but for the effective Hamiltonian, it's just a 4x4 matrix. Then furthermore, we want to find what is the additional condition for the effective Hamiltonian, so that you make sure the braiding can be non-abelian for the monofermions. So this is our idea. Okay, so first of all, we need to find the symmetries for the effective Hamiltonian. And actually, the symmetries for the effective Hamiltonian is very different from the original Hamiltonian. It depends. We have some examples. But for the particle hole symmetry, it should be satisfied for the original Hamiltonian. Actually, it is also satisfied for the effective Hamiltonian. This is easy to prove. You don't need to worry about the mathematics, but I just give you the results. However, for time-Ross symmetry, it's different. The time-Ross symmetry is protected by the original Hamiltonian, but is in general not protected by the effective Hamiltonian. This is very different. Okay, then our requirement is that we want to find a symmetry which is similar as the time-Ross symmetry, and we want the effective Hamiltonian again satisfy this symmetry. So this is our motivation. So actually, we find that suppose we have a kind of, we call this Majorana swapping symmetry. This symmetry transfers the h t to h minus t, and based on this transformation, the S also transforms the Majorana from left side to the right side, the two Kramers pairs, the 1 and 2, 1 tilde and 2 tilde. So I should write down here. So if you have this kind of additional to Majorana swapping symmetry, you find that you can show that this effect Hamiltonian should obey a new symmetry, which is the product of this the original time-Ross symmetry product this additional swapping symmetry. This is a new anti-unitary symmetry for this system. Once you have this,
what is the nature of this swapping symmetry?
It means that you have this braiding Hamiltonian, but you transfer the starting Hamiltonian to the final Hamiltonian. Do this, you swap the braiding process. Like so this braiding is actually is a time evolution from 0 to t, but actually this swapping means that you inverse this process. Inverse this process.
Okay.
Right.
So physically, how would you make h of t related to h of minus t? Is there like a
so here I should say here actually actually I say that the initial time is minus t half. The final state is t half.
Okay.
I write down it in the symmetric case. Then so let me that you should have this so in this case actually the minus t half related to the plus t half, it means that you do the transformation, actually you fully reverse your braiding process.
Yes.
Yes.
But normally you won't expect h of t and h of minus t to be unitarily related, usually. Because h of,
right.
Like one is forward braiding, another like one is clockwise braiding, other one is counterclockwise braiding.
Oh, it's not like the clockwise or anti-cross braiding. It's called you're braiding forward, but just you go back. You go back along the original path. You move forward and move backward, like this way. It's not like the clock braiding means you're braiding this way, and braiding this way. But here it means that you're braiding this way and you just go back like this. You fully reverse your braiding path, not just the clockwise or anti-clockwise. The clockwise and anti-clockwise are not opposite, right? They're not just opposite.
Sorry, I'm still a bit confused. What do you mean to reverse your braiding path? Because you actually want the final, you actually want a braid
right
at the very end. So you don't just want to reverse it, because if you reverse it, you just end up with the original configuration. Or is that, basically it's the because the typical braiding is that you do something like this. So topologically,
right,
it's different from if I do it this way.
Right.
Right. So you're still keeping with that configuration where you're still swapping them. In which case, in the forward and the backward evolution should be topologically distinct processes. Or is this like a piecewise thing? It's like if you break up into pieces, it is the same, but you're just applying the pieces in different order.
Let me see. This is really a little bit subtle. How to say that? So anyway, so mathematically, you can have a braiding which can be described by a time-dependent Hamiltonian, right? So then for this time-dependent Hamiltonian, you can always do a transformation you transform the ht to h minus t. You can always do such kind of transformation, okay? And then now the requirement that if you do this transformation, and furthermore, this transformation should also change the position of your Majorana family. So this is maybe I can write down in this way. So so suppose you have some kind of this unit transformation. It's a kind of this t goes to h minus t, and furthermore.
Now, is this h an effective Hamiltonian in your?
No, this is the original. This is the original Hamiltonian. Yeah, the original Hamiltonian, right? And then, so this. I didn't write down how this operator transform the Majorana family. Actually, then you require that this U transform this gamma 1.
Now U is time independent.
Right. Right. So this one should be should transform this gamma 2 gamma 2. And also this gamma 1 tilde transforms to gamma 2 tilde like this. Or it's 2, then it's 1, 2, and 1. So this is the definition. Yeah.
Doesn't that mean you can have a reflection symmetry between ones and the twos?
Like that, like that, like that. Yes. And in that case, maybe you can imagine that then, although maybe in one side you have local rotations, but actually in the both sides you will cancel out the local rotations. Just like that. Right.
So this is kind of like a reflection symmetry.
Like, yes, yes, yes. Actually, I should say that if you have the mirror symmetry, you should always satisfy this kind of, right, exactly.
Maybe a quick question.
Uh-huh.
Does this condition require, I mean, practically, does this condition require, we have really good control of the system because this requires HT unitary related to each other?
In principle, yes, you can control. Right. But actually, we can relax the conditions, so I can show you in later. Okay, now, once you have this kind of condition, you can based on this condition, based on the new symmetries, you see that this you can write down the effect Hamiltonian generally. If you satisfy this kind of conditions, you see that the general form for the effect Hamiltonian must satisfy this kind of form. This is the only possible form for the system. Okay, once you have this kind of effect Hamiltonian, you can show that the braiding matrix can be obtained in this way. This is you find the braiding matrix. Okay, now because for the braiding operation, you should change the position for the gamma 1 tilde and gamma 2 tilde. So this block should be 0, and this block should also be 0, right? 1 should go to 2. Okay, so then once you have this requirement, then you see that this guy should be 0. Once this guy should be 0, you see this braiding operator just is equals to this one. Okay, this will recover the original braiding operation. Okay, so then now, so this is the final condition. We should have any additional swapping symmetry. Once we have this kind of symmetry, okay, we can rigorously show that the Majorana fermion should satisfy this kind of braiding rule. Okay, now we want to do some numerical checks how well this can be satisfied. First of all, let me check this result is true, and we consider some braiding process. Suppose we consider this kind of system. We braid gamma 1 and gamma 1 tilde, gamma 2 tilde by this T junction, and we use this Hamiltonian to do the numerical simulation. So in this Hamiltonian, we have both the pure pairing and also S-well pairing, and also the spin overcoupling, which we try to consider the general case. You consider have the coupling between different copies, and you tune the chemical potential to do the braiding. And furthermore, we also consider the static disorder potentials. Okay, so sorry, I just mentioned for that condition, if you have the mirror symmetry, you can always have this kind of condition, satisfy this kind of symmetry. But actually, we can show that for this system, as long as you don't have dynamic noise, you can have this random static disorder. You can again prove that symmetry is satisfied. You should have some mathematical proof, but you can prove that. And actually, in this simulation, we also consider the random disorder potentials, and we check what happens. So we consider the braiding. We braiding twice. We're braiding 1, 2, and 2, 1 again. So for the topological case, for non-abelian braiding, it means that after full braiding, the gamma 1, all the Majorana fermions should change a sign. The gamma should go to minus gamma. This is if you get this result, is topological. It's not abelian. Okay. So now, what happened? So now we check one of the 4 Majorana fermions. We check the wave function and see how the wave function changes after full braiding. all other morphemes are the same. So then you can see that we start with this, and after full braiding, we can see the disorder. We show that after full braiding, the morphemian wave function always goes to the minus. You get a minus sign. If you increase the disorder potential, you find that more fluctuations in the middle. However, the final result always get a minus sign. So this actually shows that it doesn't matter if you have static disorder scatterings. This does not change your final result. This is quite good.
What is the red curve?
Which one?
You have two lines, right?
Red and blue.
Oh, red, blue. Oh yeah, this is the wave function. This is the projection. This is the projection to the initial morphemian wave functions. Means that if you after a braiding, it should goes to 1. This gives you how well the adiabatic condition is satisfied. If the adiabatic condition is satisfied, then after the braiding, the wave function should be anyway. The four morphemians should go back to the four morphemians. It should go back to the original subspace. But it can be a different superposition. It doesn't matter. But you should go back to the original subspace. Right. So this gives you how well the adiabatic condition is satisfied. Yeah. Okay. Good.
So the disorder has to be not like magnetic. Does not break time of the system.
Right.
Any assumption?
Oh, you can, of course. Yeah. You cannot break time of symmetry. If you break time of symmetry, everything changes. Right. That's true.
What's the form of disorder again? Just curious.
Just the onset disorder. The random onset potentials. Right. Okay. Right. And so then, okay, I just mentioned. So what about the dynamic noise? Okay. So yes, once you consider dynamic noise, it will be very different. However, it's not that bad. We can see that, suppose we can consider the dynamic noise in this based on this formalism. In general, we can write down the Hamiltonian in terms of the box states and also the morphemians. So in general, if you have dynamic noise, the dynamic noise can couple the morphemians to the box states, the box states. Okay. So now, then if the dynamic noise can induce decoherence for the braiding, namely it should induce the local coupling for the two morphemians within a single pair, right? However, you can show that just based on some calculation, you can show that the coupling between this between the two morphemians within a single pair can be obtained in this way. Actually, we can write down the exact formula. Here, I only give you the leading order coupling induced by the dynamic noise. But actually, we can obtain all the high order contributions with the result. Based on this formula, actually, we can just neglect the mathematical details, but I can give you the key result, the consequence based on this coupling. You can see that actually, even you have dynamic noise, the dynamic noise may not bring about the local mixing. If you want to mix in the local coupling between within a single Kramer's pair, the correlation function of the dynamic noise must break a dynamic time reversal symmetry. Namely, this is the correlation function of this dynamic noise. If the dynamic noise, the correlation function, say tau 1 minus tau 2 equals to tau 2 minus to tau 1, namely if the correlation function satisfies this kind of, if say tau equals to c minus tau, you can see that the local mixing vanishing, exactly vanishing. This means that, actually this is, here I only give the leading order for this coupling. Actually, we can show, even you consider all the high order couplings, this is exactly true. We can prove this result. This means Yes, if you have dynamical noise, you may induce the local coupling within a single Kramers pair. But to induce this coupling, you require the correlation function of the dynamical noise should break some symmetry, break this kind of dynamical time-reversal symmetry. Otherwise, all the local couplings still vanish. So this is interesting that actually, if you want to have the local coupling, you do need to break some symmetry, right? So
then in this sense, the swapping symmetry is a sufficient condition, not a necessary condition?
Right. It's not necessary. It's sufficient. It's not necessary. Even you have the dynamical noise, you see that if you do not break this, actually maybe this one is more general. Maybe in general, if you treat the Hamiltonian is a general time-dependent Hamiltonian, then you can see that if your Hamiltonian, the time dependence, if the correlation function does not break this dynamical symmetry, you always do not have the local coupling. You don't have local rotation. Okay. Okay, I should wrap up the results. And furthermore, the second consequence means that actually the leading mixing coupling between the Morph is from the second order transition. It's not the first order transition. This means that you can see that the two Morph they cannot couple to each other directly. Actually, due to the dynamical noise, the Morph can also couple to the box states, and also the time-reversal partner can also couple to the box states. And then based on this indirect coupling, you can induce an indirect coupling between the two Morph within a Kramers pair. So this means that the leading transition is actually contributed by the second order transition. Okay, so this is a high order correction. So we can do some numerical check, and we can show this result that, yeah, and actually we confirm all the results. If you do not break this dynamic time-reversal symmetry, it's always exactly identical or ideal. You don't have any decoherence. But if you break this dynamic symmetry, yes, you have the correction. But the leading order is proportional to the strength quartic, the power 4 of the strength of the dynamical noise. Okay, so this is exactly the second order transition contribution. So then maybe you should worry about it. Okay, anyway, if you have dynamical noise, it means that you have decoherence to the braiding. Doesn't matter. Remember, once you talk about the non-abelian for the Morph, you should always require that you don't have dynamical noise. Even for the chiral topological conductor, you have isolated Morph when you do the braiding. You should not have dynamic noise. Once you have dynamic noise, you always induce decoherence. And actually, for the chiral topological conductor, if the first order contribution to the correction to the braiding, the leading order is the first order correction. Is the first order correction. It's the second order correction. So then this means that actually the disorder, the dynamic noise is not an issue for time-reversal invariant topological conductor for the braiding. Okay. Finally, I would also say that if the noise is random, suppose you have a coherent length of the dynamic noise for the phase, then you can see that when the coherence length of the noise is less than the Majorana localization length, you can see that the decoherence is fastly suppressed, right? It's fastly suppressed. But this is quite general, quite natural. Since in that case, it means that since the noise is random, that just within the localization length of the Morph, the noise itself average to 0. In that case, the decoherence should also be suppressed. Okay, so this means that actually, okay, the non-abelian braiding for the Majorana Kramers pair should be good. In principle, it should be good. If you can realize the time-reversal invariant topological conductor, I guess it should be good to observe the non-abelian braiding for the Kramers pairs. Okay, so this is the conclusions. We introduced this concept for the symmetry-protected non-abelian braiding for the Kramers pairs, and also we confirmed the we show the sufficient conditions for this non-abelian braiding. And finally, the dynamical noise may lead to the decoherence, but it is only a second order correction, and when the dynamical time-reversal symmetry is broken. Okay, so this is the reference. Okay, thank you for your attention.